Well, good morning, everybody. Today, what we're going to do is we are going to move forward in the unit that we started a couple days ago. Now, understand that for the last couple days, we've been talking about acids and bases. We did that in lab. And then we moved on from there and we did a deeper dive last time in class, and we talked about Arrhenius and Bronsted-Lowry and conjugates and amphoterism and hydronium ion and calculating pH and calculating hydronium ion concentration. And guys, we've developed this rich foundation about acids and bases. This is then going to take you by surprise, because actually what we're going to do today is we are not going to continue that conversation about acids and bases. As you can see from the notes that you have in front of you, and all you need are those notes and something to write with, what we're going to do today is we're going to talk about reaction rate. And this has no tie backwards to acids and bases. What you're going to find out is that the tie is actually forwards. What we're going to do next time is do a lab relative to reaction rates. And then the day following that, what we're going to do is we're going to tie reaction rates and acids and bases together. And we're going to have an interesting conversation about what they have to do with each other. But we need to understand some things about reaction rate first. So guys, in order to get started, what we're going to do is we're actually going to talk about some terms that we need to share and understand as we move forward. And in order to do this, I'm going to need my writing utensils, so we'll start over. But guys, there are three terms that you need to understand the definition of. Now, the problem is that in order to demonstrate these terms to you, the best way to do it is actually visually, but you can't see me. But you will be able to hear me, and that should be sufficient. So guys, the first thing that we need to talk about is the term magnitude. Obviously, there's a space for that in your notes. And magnitude means the amount of energy that an event possesses. Now guys, what we're going to do is we are going to allow our event to be clapping. And so if we have low magnitude clapping, it kind of sounds like this. The clapping is taking place, but the collisions between my hands don't release a lot of energy. High magnitude clapping is then like this. That would be collisions or events that have high magnitude. Then guys, the next term that we need to talk about is frequency. Frequency refers to how often an event takes place. So obviously, for example, low frequency clapping would sound like this. And then of course, high frequency clapping would be many collisions in a small amount of time. So these are terms, guys, that we're going to be using throughout the rest of the day, and also importantly in the lab that we're going to do next time. So let's tuck them away for a minute, but we will be coming back to them shortly. And then guys, finally, the last term that you need to know is reaction rate. Now guys, reaction rate refers to the speed at which a reaction progresses. So let's talk about this word rate. Rate and speed in this class will be interchangeable. So let's talk about a different rate, and let's talk about heart rate. So guys, when you think of your heart rate, you're thinking about how often your heart beats in a unit of time. And typically that time unit is a minute, and then we talk about beats per minute. Well, guys, similarly, we talk about the speeds of reactions. But in order to understand this, we need to remember what reactions do. And if you remember, of course, fundamentally, reactions take reactants and turn them into products. And so when we talk about the speeds of reactions, what we're actually talking about is the speed at which the reaction, it's not going to switch, just a second. We're actually talking about the speed at which the reaction creates products. And when we measure amounts of products, that's in moles. And so the speeds of reactions are given in the units moles per second. Okay, so now that we've got these terms laid out for you, guys, at this point, what we need to do is we need to ask a question, and this question is then going to actually be the bookends for the day. So guys, I'm going to lay out this question for you, and then we're going to answer the question intelligently at the very end of the day. So, the question is this. In front of you, you have two pictures. Obviously, here on the left, you've got the picture of a crackling fire in a fireplace. And over here on the right, you've got the picture of a rusting iron or steel ring. Now, guys, the question is this. What do both of these reactions have in common? And perhaps you understand that both of these are reactions with oxygen. In order for wood to burn, we need oxygen. In order for iron to rust, we need oxygen. Now, guys, some of you may be thinking, wait a second, doesn't water rust when it gets wet? And doesn't metal rust when it gets wet? And doesn't metal rust when it's around salts? And the answer is no. When metal rusts, it is not a reaction with water and it's not a reaction with salt. Salt and water encourage the reaction, but ultimately it's actually a reaction with oxygen. So guys, both of these then, as we now understand, are reactions with oxygen. Here then becomes the question. Imagine that we come back 24 hours later and we come back to the fire. Guys, when we come back 24 hours later, what's the fire going to look like? Well, obviously, 24 hours later, we run out of limiting reactant, which is the wood, and we just have a pile of ash and the reaction's over. Well, guys, what's it going to look like if we come back 24 hours later and we look at this ring? Well, in order to talk about this, we need to understand something. 100 years ago, when the farmer that built the barn that this ring is attached to hung that ring on this barn, it did not look like that. It was probably a shiny piece of black metal that he had got from a metalsmith, a blacksmith, and he, with great pride, attached it to the side of his barn. It didn't look like this. But guys, over the years and the decades, it's been rusting. But guys, the question then is this. What's this going to look like 24 hours later? And the answer is the same. But guys, we also understand that that's not technically true. Because if it did look the same, it wouldn't look different 100 years later. So it is changing, but it's changing imperceivably. So now, guys, let's tie this to rate. Fire is a reaction that goes very quickly, a high rate. The rusting of metal is a reaction that goes much more slowly, a slower rate. So then, guys, the question becomes this. Why do some reactions go really fast, and why do some reactions go slower? Now, guys, in order to answer that question, switching to the next slide, we have got to talk about an important question. Fast or slow, what has to happen for a reaction to take place? And guys, the answer is so simple that almost it's obvious, and many times people miss the answer. The answer is this. If you want wood to burn, react with oxygen, the wood and the oxygen have got to collide. If you want iron to rust to react with oxygen, the iron and the rust have got to collide. And guys, if you think about it, that's the way a fire extinguisher works. If you've got a fire extinguisher, what you're actually doing is this fire extinguisher actually coats, let's see if I can switch colors. Am I in red? So blue. What happens is the fire extinguisher actually coats the fire, the fuel, not the fire, coats the fuel with a substance, many times a powder, that doesn't allow oxygen to get to the wood anymore. The wood and the oxygen can no longer collide and the fire goes out because you have literally smothered the fire. You have prevented the collision collisions between the fire or between the oxygen and the wood. That's how a fire extinguisher works. So guys, again, the important big idea is that in order for a reaction to take place, there has to be a collision. Okay, with that understanding then, let's move on. So guys, in order for a reaction to take place, there has to be a collision. We call this the collision theory of reaction rates, because it's not a theory. This is the way that this works. But it brings up some interesting ideas, because guys, not all collisions are effective. See, in order for a reaction to take place, the reactants have got to collide. But that's not enough. Not every collision creates a reaction. So guys, these collisions must happen with enough energy to break the bonds within the reactants so that they can create products. So guys, the question becomes, what happens if they don't hit with enough energy? And the answer is nothing. It's as if the reaction never took place. So if they don't hit with enough energy, the reaction does not proceed. So guys, again, not all of these collisions are effective. And if they don't hit hard enough, no reaction takes place. So guys, this then leads us to what is probably sort of an interesting and obvious question. How hard do they have to hit? Well, we know that that's hard enough to break bonds, but how hard is that? So guys, in order to answer this question, let's talk about the answer. How hard do these things have to hit? And the answer to that question is what we call activation energy. Moving on to the next slide. So what is activation energy? Well, guys, activation energy is the minimum amount of energy that is needed for a reaction to take place. Now, guys, when we talk about this, we are going to conceptualize this as being a hump that exists between the reactants and products. Now, the idea is this. How does this relate to the speed of the reaction? And the answer is this. The more collisions that get over the hump, the faster the reaction goes. And you're like, wait a minute, I'm not exactly sure what that means. Well, guys, in order to talk about this, let's talk about what might be a familiar setting for you, which is a putt-putt golf course. And guys, if you have played this particular hole on a putt-putt golf course, you may know the frustration of this hole. Now guys, notice right here we have a collision. Now this is where the analogy breaks down a little bit, because in order for this analogy to actually hold true, the club would have to collide with the ball, and then the club and the ball would have to move forward across the green. We're just going to keep track of the ball. So guys, the idea is this. If the club hits the ball, but it doesn't hit the ball hard enough to get over the hump, well, what happens? Well, the ball rolls to right there, and guys, it can't make it over the hump, and so as a result, the ball just rolls right back down to your feet as if no collision had ever taken place. Guys, these are what are called ineffective collisions. They're collisions that don't get over the hump. So what do we need to do to get more collisions over the hump? Well, guys, obviously the answer is this has got to hit with more energy. But guys, this is where things get interesting. This is actually a magic putt-putt course. And the way that it works is if the ball makes it to the top of the hump, and guys, understand the height of this hump represents what we call activation energy. You may want to write that down. Guys, if the ball gets to the top of the hump, it automatically rolls back down and it goes into the cup. This is analogous. This is the representation of reaction rate. So guys, the idea is this. The purpose of the reaction is to put balls in the cup. In order for balls to go into the cup, they must collide with enough energy to get over the activation energy hump. When they do, they immediately go to products, and the more balls that go into the hole, products, the faster the reaction goes. Now, guys, let's carry this analogy one more step. What could we do as a putt-putt golfer to get more balls to go over the hump? And guys, as you're thinking about this, maybe you're thinking back to some of the things that we talked about initially. Well, guys, obviously, one of the things that we can do to get more balls over the hump is we can make sure that fewer balls get stuck right there and roll back down. So what do we need to do? Well, what we need to do is we need these things to collide harder. And the harder the collisions, the more of the collisions that get over the hump, and as a result, the faster the reaction goes. But guys, remember what we said. We are not going to use the word harder. What word are we going to use for collisions that involve more energy? And hopefully you're right now saying the word magnitude. So guys, we need higher magnitude collisions. And guys, that's certainly one thing we can do to get more balls over the hump. But there's another thing that we can do. Imagine that we have one collision that's really hard and it goes over the hump and it goes into the cup. Then we go and we grab lunch and we come back an hour later and we hit another ball over the hump really hard. And it goes in the cup. Now understand, guys, we're putting every single collision in the cup, but the reaction still isn't fast because we went to lunch in between hits. So guys, what's the other thing we can do? Well, we can hit more balls over the hump in any space of time. So it's hit a ball, hit a ball, hit a ball, hit a ball, and hit them hard. So we need to hit these balls more often. But guys, we are not going to use the word often to describe what we're talking about. What's the word we're going to use? We're going to talk about frequency. And so what can we do then to make the reaction go faster? And we're going to talk about this more in a minute. We can increase the magnitude of the collisions, hit harder, and we can increase, or we could increase the frequency of the collisions, make them hit more often. Now, guys, a little bit of foreshadowing. This is exactly what we're going to do in lab next time. You are going to go to lab and you're going to carry out a chemical reaction given my instructions, and you're going to time it. Then what you're going to do is you're going to run exactly the same reaction 3 more times. And you are going to have the freedom to change whatever you want about that reaction. You're going to talk with your lab partners about this. You're going to agree upon the changes, and then you're going to carry them out 3 times. And each time you carry out this reaction, your goal is to make the reaction go faster. How do you do that? It's about frequency and magnitude. And we're going to talk more about this in a minute. But guys, what we need to do first is we need to get away from this idea of putt-putt golf. And we need to move this into the world of reality. And we need to talk about some chemistry principles. Now, guys, in order to do this, I'm going to change. Neither red nor blue works out very well. I'm just going to go black. All right. So, guys, what we need to do is we need to understand this diagram, this graph, if you will. But you're going to have to be able to reproduce this. So guys, let's do this together. So what I need you to do is maybe highlight, if that's helpful, the vertical axis, and understand the y-axis is energy. Low energy is at the bottom, 0 energy, and high energy is up. I would encourage you to label that. Then guys, over here on the bottom, we have reaction progress. Functionally, that just means time. Uh-oh. Oh, it wants to do a Java update. Sorry about that, guys. That's time. And so time down here is the beginning, and time over here is later. Okay, so left to right, we're moving through time. Bottom to top, we're increasing energy. Now, guys, with those pieces labeled, notice what we've got. We've got reactants, we've got products, and then we have the same hump that we had on the putt-putt course, and that represents activation energy. Now, guys, what we need to do is let's put this in a real-world setting. And I would encourage you to do this with me. So, guys, let's talk about some real-world reactants. And one of our real-world reactants is going to be CH4, which I drew the Lewis dot structure on the board. Then, guys, our other reactant is going to be oxygen, which we understand is diatomic. And you may remember from drawing Lewis dot structures that oxygen is double bonded, and it looks like this. Okay, so now let's talk about this reaction. So what kind of reaction is this? Well, this is, all right. This is a combustion reaction, not single or double displacement, it's a combustion reaction. And guys, when we talk about combustion reactions, we know our products. They are carbon dioxide and water. But now, guys, let's draw the Lewis dot structures for these. Carbon dioxide is well, let me move that down a little so it's not misleading. So, guys, I'm going to write them off to the right. So, carbon dioxide is a carbon double bonded to two oxygens. Looks like this. And then, guys, obviously water is our good bent friend H2O. Okay, so now at this point, guys, this brings up a really interesting question. What has to happen from the left to the right in order for reactants to turn into products? What has to happen to the CH4 molecule and what has to happen to the O2 molecule in order for them to turn into carbon dioxide and water? And guys, the answer is the molecules on the left have got to break apart. The carbon has to detach from the hydrogen and the two oxygens have to detach from each other. So how do we do that? Well, guys, we add energy. That makes this endothermic. Now, guys, let's stretch a little bit. When do you do this reaction of CH4 reacting with oxygen? Answer, Bunsen burner. Now, guys, what does it take to light your Bunsen burner? And the answer is your striker. And guys, literally what happens are the sparks from your striker actually add a little bit of energy to the CH4 and the oxygen in the air. And it breaks a few of these molecules apart. But guys, you'll notice you don't have to continue to use the striker in order to keep this reaction going. Why not? We'll look at that in a second. So we add some energy and the carbons and the hydrogens break apart and the oxygens break apart. And as that happens, the energy goes up. And up here at the very top, we now have carbons and hydrogens and oxygens all busted apart. Now, guys, understand that if there's not enough energy in those collisions to break the CH4 and the oxygen apart, guys, no reaction will happen. It's kind of like the difference between a fender bender and a freeway accident. Guys, if you tap bumpers with somebody in the parking lot, chances are good nothing's going to change because the collision is such low energy that it's just no harm, no foul. Now, guys, understand if you've got two cars going 80 miles an hour in the freeway and they collide head to head, those cars are going to blow apart, right? Well, guys, that's what's happening here. We need enough energy for these molecules literally to blow apart. That's what the spark does, is it gives them a little bit of energy that allows them to collide harder and blows them apart. So if they have enough energy to blow apart, we end up with carbons, hydrogens, and oxygens. These carbons, hydrogens, and oxygens can then bond together. And as these bonds form, energy is released. Energy goes into break bonds. Energy comes out when bonds are formed. So that makes this exothermic. And as that energy is released, as these bonds form, we end up with these molecules forming. So now, guys, the question is this. When these bonds form, where does the energy go? And the answer is interesting. Some of the energy actually recycles backwards and breaks more of the CH4 and the oxygens apart. But that's not where most of the energy goes. Most of the energy goes away as heat, and that's the heat that we use to heat our homes and boil water and everything else. So guys, literally the energy of a Bunsen burner that we use to heat water is simply the energy that's released when carbons and hydrogens and oxygens bond together. And guys, that energy is actually represented by this height. This height right here is the change in energy when this reaction takes place. Sorry, not quite that height. I went a little bit too low. This height right here. The difference between reactants and products, notice it's going down. That means that energy is released, and that is the energy that we experience as warming our homes or boiling water. So energy goes in as the bonds break, energy comes out as the bonds form, and that then explains activation energy, because enough energy has to go in to get over the hump, and when they do, in this case we get carbon, hydrogen, oxygen, they form products all on their own. Okay, so guys, that's the fundamental ideas behind activation energy and what that hump means. So now, guys, the question becomes this. What can we do to get more collisions over the hump? Hoping my board doesn't freak out. Guys, what can we do to get more collisions over the hump? And the answer is this. What we can do is we can either change the magnitude of the collisions, or we can change the frequency of the collisions. Higher magnitude, more energy, more get over the hump. Higher frequency, more collisions per time, more get over the hump. Rate goes faster. So guys, how do we do this? There are three ways that we can affect the magnitude or frequency of collisions. Guys, be ready to write stuff down. So one of the things we can do is we can change the temperature. As the temperature goes up, the rate goes up. Guys, you understand that this is why we have refrigerators. If higher temperature makes reactions go faster, lower temperature makes reactions go slower. So guys, what happens is when we buy food, it is rotting all the time. The clock is ticking. So we want to be able to eat our food before it rots. So what do? We slow down the rotting process by sticking the food in the fridge. This cools it down, slowing down the reactions that cause your food to rot. And as a result, you can typically eat it before it rots. Now understand, if you forget something in the back of the fridge for 2 weeks, it's going to be nasty. So it doesn't shut it down, it just slows it down. If you want to more shut it down, put it in the freezer. Because at that point, it's cold enough that the reaction's going slow enough that typically things can be saved almost indefinitely. Okay, so the question becomes this then, why? Why is it that heating stuff up makes it go faster, cooling it down makes it go slower? Well, guys, it's going to be one of two things. It's either going to be the frequency of the collisions, or the magnitude of the collision. So which one is it? Well, guys, let's talk. So guys, the question becomes, what's the difference between hot and cold? So on the left we have hot, on the right we have cold. Guys, fundamentally, what's the difference between hot and cold? And obviously the answer is cold things, turtle, cold things are moving slow, and hot things are moving like creepy naked guy, they're moving fast. So guys, here's the deal. If we have hot substances, temperature up, if we have hot substances, they are moving more quickly. Now guys, if they're moving faster, does that change the frequency of the collisions or the magnitude of the collision? Let's do frequency first. If you're moving faster, will you collide more frequently? And guys, the answer is obviously yes. If you are moving if you're moving faster, you will collide more frequently. But what about harder, higher energy, higher magnitude? And guys, the answer is also yes. It's like the cars in collisions. If you're moving 1 mile an hour and you collide, not a lot of energy. If you're going 80 miles an hour, things change. So guys, temperature changes both the frequency and the magnitude of the collisions. Okay, so moving on, what are other things we can do to change the rate of a reaction? Well, the next one is concentration. As the concentration of the reactants goes up, the rate goes up. Again, folks, the question is why? Well, the answer has to be frequency or magnitude of collisions. So let's look at a real-world example. Guys, on the left, this is Cornhusker Stadium on any Saturday during the fall. Guys, during football season, Cornhusker Stadium actually becomes the 4th largest city in Nebraska. More than 100,000 people in this stadium. In order to get tickets, you have to be left tickets in your will, like it's a big deal. Then guys, what about this? Over on the right, we actually have a picture that was taken from the KSL building in Salt Lake. This is actually the Gallivan Center. During lunch, people wandering around, meeting with folks for lunch. So guys, here's the question. On the left, we have a very high concentration environment. On the right, we have a low concentration environment. Now guys, imagine that we could put these pictures into motion. So if we put these pictures into motion, will these people collide more frequently based upon concentration? So will the people on the left collide with people more frequently than the people on the right? High to low concentration. Because the answer is obviously yes. The higher the concentration, the more frequently collisions will take place. So this is definitely a frequency issue. Now, is it a magnitude issue? And guys, interestingly, the answer is no. Just because people are more tightly packed together doesn't mean they're going to hit harder. As a matter of fact, if the people on the right were sprinting, they would actually hit each other harder than the people on the left. So it is not a magnitude issue, it's only a frequency issue. Okay, so what about other ways we can affect this? Guys, the next is surface area. The higher the surface area, the faster the reaction goes. Again, why? Is it frequency or magnitude of collisions? Now, guys, in order to answer that question, let's talk about the difference between a log and kindling. So, guys, if we want to start a fire, you'd be a fool if you took a match and if you held a match to a pile of firewood. Obviously, without gasoline, this is not going to catch on fire. But, guys, what about this? Why on earth does making kindling make fire happen more easily, whereas logs, which are made of the same things, we can't light? And guys, the answer is surface area. Imagine this. Imagine if we were to focus on this log right here. Now guys, imagine the surface area of the log. The surface area of the log is this end, and then a similar end at the other end, and then it's the face here, the face here, the face there. That's the surface area of that log. Now guys, imagine if we take an axe and we split this log in half. Now we've just exposed surface area that wasn't there before. And if we keep doing that and 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 doing that, eventually we end up with kindling. And what we've done is we have now created so much surface area that there are so many places for the oxygen in the wood to collide that the reaction is more likely to take place faster, and that's why kindling works. Now again, guys, the question, is this a matter of frequency or magnitude? Does cutting up a log make the oxygen and the wood hit harder? The answer is no. This isn't a magnitude issue. Guys, this is a frequency issue. More surface area, more frequent collisions. Okay, so now guys, we've got one more to talk about. This is interesting, and this is how we're going to also wrap up the day. Because there's one other way that you can make a reaction faster. It's called a catalyst. Now guys, a catalyst is a substance which increases the speed of a reaction without being consumed during the reaction. Guys, we will not talk about this anymore in general chemistry, but one of my favorite days in AP is when we get to talk about catalysts. Guys, this is fascinating beyond belief. It's really, really cool. But guys, here's the deal. In this class, you will not have access to catalysts. So when you do the lab next time, adding a catalyst will not be an option because the reaction that you will be doing 4 times is not a reaction for which a catalyst exists. So that's going to be off the table. But guys, how do catalysts work? And this is really interesting. Guys, catalysts do not change the frequency or the magnitude of the collision. So you're going, wait a minute. You said that the way to change the rate of a reaction, getting more collisions over the hump, is by making them hit more often frequency or making them hit harder magnitude. Not quite true. There's another thing that we can do to get more collisions to go over the hump. Guys, that other thing that we can do is we can lower the hump. And that's what catalysts do. They create a brand new way for the reaction to take place, and this brand new way has a lower hump. So guys, imagine it. If you look at this, this was our reaction pathway. And guys, truth be told, the reaction of methane and oxygen also doesn't have a catalyst. But the theory is this. Adding a catalyst to this reaction actually drops the activation energy hump. Because the activation energy hump is lower, more collisions get over the hump, and that makes the reaction go faster without changing the frequency or the magnitude of the collisions. Okay, so guys, there you have it. What we are now ready to do is finish the conversation that we started. So guys, coming back to this slide, last slide in your notes, we asked the question why. These are both reactions with oxygen. Why does the reaction on the left go so much faster? Because what I'd like you to do is I would like you to discuss this question only with the person sitting next to you. Take a second and chat. Okay, now that you've had the opportunity to talk about this, let's talk together about why the reaction on the left is faster. So guys, let's talk about our options. In order for a reaction to go faster, it's temperature, concentration, surface area, and catalysts. So guys, let's do temperature first. Does it make sense that the reaction on the left is going faster? Well, yes. It's hotter, and because the reaction is hotter, this one goes faster because of temperature. Now guys, interestingly, the reaction on the left, as this rusts, it is actually releasing heat as well. As the iron bonds to the oxygen, it is actually releasing heat. It's just so small that it's hard to perceive. If you want to learn more about this, Google how hot packs work. You know those packs that you can shove in your gloves and mittens to keep your hands warm? Because in order to make those work, you actually rip the package open, and when you do, oxygen can get in. Briefly, we'll talk about it. Guys, inside of that package is actually iron and a catalyst. And literally what's happening is the iron is reacting with the oxygen in the air, but now it's reacting so quickly that you can feel the heat and warms your hands. Now guys, how do they get that to happen? Partially because they use a catalyst. But the other reason is because they grind up the iron into little filings, little shavings of iron. Now guys, why would that make the reaction go faster? Surface area. Okay, so now let's talk about number 2. Concentration. Is there a concentration issue going on here? And guys, interestingly, the answer is yes, but it's not what you think. The concentration issue is actually right here. This is not a high concentration. This is a low concentration. And it's not because of what you think. Guys, this ring is surrounded by oxygen. But remember, for the reaction to happen, the oxygen has got to be able to hit the iron. But guys, when the oxygen hits the ring, do you see that it's not hitting the iron? Actually, what it's hitting is the iron that is already rusted. As metal rusts, it actually becomes coated in rust. And that rust keeps the metal underneath from being hit by the oxygen. And as a result, it doesn't rust as quickly because the concentration of available iron is actually lower. And so this is not only then a concentration issue. So we do have a concentration issue going on over here because the concentration is low because there's not that much iron available to rust because it's coated in rust. Guys, this is also a surface area issue. And it works in 2 ways. Obviously, there's a ton of surface area over here, but guys, also on the right, not only is there not as much surface area on this ring, but the surface area that's available to react is even smaller because of the rust coating, which is both a concentration and a surface area issue. Okay, so one other thing that contributes to the reaction on the left being faster, and this is already in your notes. But guys, this is not a catalyst issue, but it is an activation energy issue. So guys, if we could look at the energy diagrams for these reactions, they're very, very different. So the activation energy for the reaction on the left, the activation energy hump is actually fairly low. Guys, the activation energy hump, sorry, I drew that wrong. My fault. The activation energy hump for the reaction on the right is relatively low. The activation energy for the on the left. The activation energy for the reaction on the left is relatively low. The activation energy for the reaction on the right is much higher. Why would that be true? Well, guys, remember, activation energy hump is the amount of energy needed to break the bonds. But guys, what is this made of? It's made of iron, and iron is very strong. What makes it strong? Strong bonds. And so if iron is very strong, it's hard to break apart. Therefore, we have to add more energy to get it to break apart, and therefore the activation energy hump is higher. So guys, in a very short period of time, you guys learned an amazing amount of stuff. So here's what we're going to do for the remainder of the day. We are going to do homework assignment number 2. As you look at homework assignment number 2, you will notice that it is all qualitative. It's all ideas. Now, guys, understand as you engage with these ideas, what you're actually doing is lab prep for the next class period. So guys, what we're going to do is this. We're going to spend the rest of the day today productively answering the questions on the second homework assignment. If you need to consult with somebody, you're welcome to chat with the person next to you appropriately. And then guys, we will review this homework assignment when I see you next. We'll record scores. And then guys, we will quickly get you into lab so that you can stress test the ideas that you were writing down in your homework. So guys, let's get to work. Let's get as much of this done as we possibly can. And we'll see you next time.